So first, I'd like to summarize what has been happening at Arecibo Observatory for observations of potentially hazardous asteroids. So summarizing the status of Arecibo, it's the largest, the most sensitive, the most powerful, the most active planetary radar in the world. It's a 305-meter dish, meaning you have 20 acres of collecting area to work with. And at Arecibo, there's a S-band transmitter with a maximum power output of 1 megawatt, and that's operating at about 13 centimeters or 2.4 gigahertz. And it affords us resolution of up to as fine as 7.5 meters per pixel, which you'll see later. So all that sensitivity means that we are capable of detecting any potentially hazardous asteroid that comes within 0.05 AU, or about 20 lunar distances of Earth. And any detection made with radar provides you with extremely precise line of sight velocity astrometry at the level of about 1 part in 10 million. And it also gives you a measurement of the rotation rate, the instantaneous rotation rate, rather than watching the entire rotation period. And as you have higher signal, you can start to get radar images and learn more about the sizes and shapes of these bodies. And that's what I want to summarize here today. So quickly, some statistics of what's been happening at Arecibo. This is a bit of a busy plot, but you have, I guess we don't have, oops. Oh, you can, there it is. So you've got years across the horizontal and number of near-Earth asteroids on the vertical. This doesn't seem to be working well. But the gray areas you're seeing there are the number of NEAs detected per year. We're sort of at a range of about 60 to 80 per year right now. But for potentially hazardous asteroids, it's the hatched part of the plot there. Potentially hazardous asteroids make up about 40% of all detections at Arecibo. To date, there's been more than 300 different potentially hazardous asteroids observed. That's about 15% of the PHA population. And that includes about 50 PHAs since the last PDC meeting in Tokyo. And just for this year, of course, we've only had 4 months, but there have been 8 PHAs detected out of about 31 total asteroids detected at Arecibo. Okay, so I'm going to be showing a lot of radar images. So the radar image on the right is of Phaethon, which is well known as an activated asteroid. It's the flyby target of Destiny Plus, the parent body of the Geminids. So in this radar image, you have the radar illuminating the asteroid from the top of the image. So range from the observer is increasing downward from the leading edge of the asteroid back. This is 75 meters per pixel in this image. So not the highest resolution we can do, but it certainly gives you a lot of information about Phaethon itself. The important thing about radar images is the horizontal dimension is speed. It's not exactly physical space, but it's related. So what you see in here is the object appearing to rotate counterclockwise. This is roughly 1 full rotation stitched together over several days of observations of Phaethon in December of 2017. This happened to be the first object after Hurricane Maria, so that was a pretty big deal. And what we were able to find about Phaethon is it's roughly spheroidal in shape. Its shape is going to look very similar to Bennu, but it's 10 times bigger in diameter or 1,000 times bigger in volume. And the other very important thing we learned about Phaethon is it appears to be much larger than ever thought before. The equatorial dimensions are about 6 kilometers in diameter. And if it has a Bennu-like shape, the effective spherical diameter is about 5.7 kilometers. This is much larger than has been predicted from infrared observations, which expected the diameter to be about 5.1 kilometers. And this is a big deal if you have to mitigate a possible impact threat, because that's 40% larger in volume, 40% larger in mass, 40% larger in impact energy. So that's extremely interesting to get this sort of ground truth size measurement for an asteroid. So the last object we observed before Hurricane Maria was 3122 Florence. So we have a series of radar images here. You can see Florence here in the center. It's more than 4 kilometers in diameter, and it rotates rather fast near the rubble pile breakup limit. really interesting thing is you spot two moons. There's one here, and there's one down here, and you can see them move from frame to frame. This one's moving downward, and this one's moving upward, and you can track them through this animation. There goes one. Here comes one up the image. There's the other one. So this was the third triple system ever found. All of them have been discovered by radar. And optical light curves never would have seen these satellites. The size difference is just too great. You would never notice a eclipse or occultation event between them. So, of course, finding unknown satellites would certainly make a mitigation effort much more difficult. And last summer we saw 2017 YE5. When it was originally imaged with the Goldstone radar, it sort of had this double lobe sort of peanut shape that we see pretty often among near-Earth asteroids. But it was never clear if it was two connected objects or two separated objects. When Arecibo teamed up with the Green Bank telescope in West Virginia, we got sufficient resolution in the velocity dimension to separate the two objects. And you can very clearly tell that this is two similar sized objects in orbit about each other rather than a contact binary. It was eventually detected, eclipse events were eventually detected between the bodies optically, but not until a month later after the radar. So that would certainly be a unique challenge for impact mitigation. You fly out to an asteroid thinking it's going to be one object, 1 point something kilometers across, and find out it's two objects, 1 kilometer across. And I know this is an Arecibo talk, but this is some, I couldn't pass up showing these Goldstone images of asteroid 2003 SD220. This object, with Goldstone, they can get down to higher resolution than Arecibo, 3.75 meters per pixel. This is an extremely slow rotating object. These are snapshots from each day where it only rotates a tiny fraction of a rotation. It takes 285 hours or about 12 days for this asteroid to rotate, but just incredible amounts of detail. It's not just two lobes, it's got this sort of ridge between them, and you can trace this ridge to right there, and then it rotates to here. So this is a tumbling asteroid. It's not just rotating, it's also rolling around its long axis, and it's very obvious from the radar images. So these are the images from Arecibo and Green Bank from a couple days after the Goldstone images. So it's rotated a little bit further. Before it was going this way, now it's pointed this way. And you can see the ridge sort of disappears. You don't see it as prominently. Something else pops out here. There's like a raised facet there. And then a really strange thing is this blank spot. There's just nothing reflecting the radar on this part of the asteroid. We have never seen anything like that before. Literally, the pixel values here are the same as the background. There's just nothing reflecting from a huge fraction of this asteroid, like a scoop has been taken out of it. And I wanted to touch on 1999 KW4 because it's the focus of the next IWAN observing campaign starting next month. This is an image from 2001 where the satellite was discovered, 15-meter resolution in these images. And KW4 became the sort of prototypical near-Earth asteroid binary. So we're preparing for that next month. It won't be, the images won't be the same as in 2001. They will probably be a bit more similar to this image from 2018. You can still clearly see the primary. You can certainly measure the size of it. You can see the secondary, and we'll be able to watch it go around in its orbit. So we expect to be able to constrain the size, shape, the orbit, the sort of mass, density, all sorts of things based on the images we get this year. So to summarize, radar is a powerful method for providing not just precise astrometry, but also constraining the size, shape, and rotation states of small bodies. Arecibo actively is prioritizing potentially hazardous asteroids for radar observations. And radar reveals properties of small bodies that can be really complicating factors for impact mitigation. As I've showed, all these really interesting objects have something about them that would be difficult for a mitigation scenario. Radar can easily pick out binaries. About 15% of large NEOs are binaries, and radar has either has discovered more than 70% of them and detected 90% of them. And besides binaries, you can have equal mass binaries or triples, each of those at about 1% of the population. So they would be a rare event, but they are something you should certainly consider if you had to mitigate an impact. And then, I completely forgot to mention about SD220. NEOWISE initially estimated SD220 was about 0.8 kilometers in diameter, and we found the long axis was 2.5 kilometers. So there's a huge difference there, and something we need to look into further, the measurements made by, say, NEOWISE or other infrared capabilities compared to radar. So that'll be something for future work.
Okay, thank you. What Benzo is standing waiting.
Yeah. Do you know the MOID for SD220?
I do not know it offhand, but
Well, I'll point out that if you look at a 1998 paper by Derek Richardson that shows shape of objects that get tidally stressed by the Earth, it's a dead ringer for figure 1 or figure 2 in the Richardson 98 paper.
Yes, Amy.
Hey, Patrick, we've talked about this object before, but it's a 220 is an interesting one. Going back and looking at the NEOWISE data, it has one of the largest amplitude light curves that I've ever seen. It's almost 2 magnitudes at 4.5 microns, which is substantial. And it turns out it has a really long rotation period too, about 11 days or something. So it's pretty extraordinary.
right, it's actually really interesting. It looks like the initial measurement from NEOWISE, you happened to catch it end on, but then there was enough data that you saw a thermal light curve over time. So you would have backed out that it was highly elongated and it had a long period. You could have said something about that.
I think so we did publish the high amplitude, but I think one of the things we want to look at is this is a really neat target for thermophysical modeling. If you combine the IR data with the radar shape, it should be interesting.
Yes, that'll be interesting. Any other questions? Oh, yes, Dave Tholen, way in the back there. You want to just shout or somebody bring?
It might be more of a question for Joe, but when you have a binary with equal sizes like that, when you're doing thermal models, I expect the assumption is that it's single body, and if it's actually 2 bodies like that, it's obviously going to affect the results. So I'm wondering if there might be some outlier results within the NEOWISE that might be more easily explained by assuming it's 2 bodies rather than a single body.
Yeah, so the zeroth order assumption is everything's a spherical cow. And as Amy indicated, large light curve amplitudes can indicate that's a bad assumption and that you need to do a more detailed thermophysical model, for instance, or use an ellipsoidal model. But yeah, so that's why we get a 0.8 kilometers. We smush it into a sphere and say, what's the spherical equivalent diameter? When you have more information saying it's elongated, you have to start to do more detailed modeling.
I would comment the equal mass binaries tend to be split by several radii of the bodies so that they're not contact, they're rather separated. And so the thermal properties are not going to be shadowing each other typically so much. So I don't know just how much effect that
Or they'll be heating each other. So,
yeah,
you know, it gets really complicated really fast in like a nearby equal mass binary.
It's a fun exercise for sure.
Sure.
I think we have to move on now.